There we are. Okay, so today, Friday, we're going to be finishing what is section 2.3 in Tau. This section in Tau is fine to read. We're basically following it, but there will be lecture notes as well. Okay, so last time we looked at continuous functions and compactness, and our big theorem was that the continuous image of a compact set is compact. Okay, and then we looked at those two consequences of that. And remember, the big one was the extreme value theorem. Okay. Now, our topic is uniform continuity. Now, we looked at uniform continuity a little bit last semester, so let's just recall the definition. Okay. Except we're not just going to recall the definition, we'll just write it for arbitrary metric spaces. Okay, and the modification is exactly what you would think it should be. You got a couple metric spaces. And you've got a function. And this function is uniformly continuous. Now, remember, continuity was for every point, and every epsilon there exists a delta. And then uniform continuity, the whole point is that the delta that delta does not depend on the point. Okay, so for every epsilon, there exists a delta such that it works at every point. So such that if the points A and X in the domain satisfy the closeness requirement, so they have to be within delta in the domain, then their images have to be within epsilon. So really the only thing that moves in this definition from the definition of continuity is that A. We used to have, where do we know? I think we put it there, right? For every A and every epsilon, right? Oh, I'm sorry, yeah, we usually define continuity at A. And therefore it's, yeah, for every epsilon, there is a delta, so that if the point X is that close to A, then the images are that close together. Okay? Like I just said, for continuity, we give a definition of continuity at a point. For uniform continuity, there is no such definition. Okay? It wouldn't make sense to be uniformly continuous at a single point. Now, what would make sense is to be uniformly continuous at a set. Okay, so if we took a subset of the domain, we could talk about being uniformly continuous on that set. Okay, but what we would do is we would just restrict our domain to that set. And then we'd talk about being uniformly continuous with that domain. Okay, does that make sense? So we could talk about being uniformly continuous on a set, but we can already do that with this definition. Okay. Now, when we did continuity, our first result, was the very important topological version of continuity. A function is continuous if and only if the preimage of every open set is open. Okay, everybody remember that definition, and that's the one, I mean, we've been seeing examples of how that's so useful. Okay, we're not going to do that here because there is no such definition. Okay, so we cannot give a purely kind of topological definition of uniform continuity. So what I mean is you can't give a definition of uniform continuity that's only in terms of what are the open sets, you know, what does the function do to open sets. Okay, it just doesn't exist. So this is a function. This is a definition that really only works in metric spaces. Okay, or if you want, there's a slightly more general setting in which you can do it in. Okay, but you can't do it in topological spaces. Okay, everybody with me so far? Any questions that have come up?
Just the same as before.
What's that?
This is just the same as last semester, except it's metric spaces.
Yeah, so that changed and that changed. Yeah, now we're looking at distances in the metric spaces. Yep. Do we have, yeah, okay. I think we've got a short lecture today. Although every time I say that, I seem to be wrong, but. Let's do an example. This is from, and we're just going to do it on the real line. So this is an example from last semester. Let's see if we remember how to do it. Okay. Here's my function. It's going to be from the reals with the standard metric to the reals with the standard metric. And is that uniformly continuous or not uniformly continuous? Not. I guess we should go over here. This is a non-example of uniform continuity. Okay, how do we show it's not uniformly continuous?
Take a particular epsilon, that maybe 1/2. It's one of our bigger numbers.
We like 1 even better, don't we? Okay, so epsilon is 1. Now we have to defeat all the deltas. But we get to pick the 2 points. Anyone remember what what points we want to look at? I wouldn't expect you to be able to do this off the top of your head. You do have to fiddle around a little bit, but here are points that work. If we let A be 2 over delta, and xb 2 over delta plus delta over 2. Then, and now remember, this is just standard metric, so we're looking at distance in R, so that's the absolute value of the difference. We can see that that's the distance between the 2 points is delta over 2, that's less than epsilon. But now we just have to compute what the function is at these points. Okay, we compute the distance between the function values. And we get 2 plus delta squared over 4. It's certainly bigger than epsilon, which we set to be equal to 1. Okay? So, this function is not uniformly continuous. How do we make it uniformly continuous? Benjamin asked in the chat, we can tell that it's not uniformly continuous because the domain is all of R. What do you mean by that, Benjamin?
I think maybe forgetting something from last semester. I thought there was something to do with the range being, or the domain being infinite that led to problems with regards to uniform continuity. I have to review that.
Yeah.
Something last semester though.
I think it was something that, again, if you restrict the domain to just like a closed and bounded interval, then the function will be, and if you restrict the domain of a continuous function to a closed and bounded interval, then you will get a uniformly continuous function.
That's what I was fishing for. If we restrict the domain to be, I believe what we proved last semester is a closed and bounded interval. Then the same function is uniformly continuous. Okay. In the chat, Daniel pointed out, yes, constant functions are uniformly continuous. Yeah, that wasn't quite what I was fishing for. But that is also a true fact. The identity function is always uniformly continuous. Things like that too. Linear functions always uniformly continuous. But x squared, not uniformly continuous on the real line, but as we saw last semester, if we restrict the domain, then we get our uniform continuity. Now, we're going to be proving one theorem today. If you've been paying attention, I think you can probably guess what the theorem is. And Zach beat you all to it. He beat me to asking the question. Yep. If our domain is compact, then we're uniformly continuous. And you should be able to guess because you look at this closed and bounded interval. And whenever you saw that last semester, this semester, the word is compact. Okay, so again, this is one more piece of evidence that compactness is a useful notion that generalizes the closed and bounded intervals of the real line. Okay?
We always have that a compact set is closed and bounded.
Yep.
But we don't always have that closed and bounded set is compact. Does this result only hold for compact, or is it really just the closed and boundedness that makes it work?
It's only compact.
Okay.
Yeah. Yeah, so in the, on the real line, in R squared, in R cubed, all this, closed and bounded is the same as compact. But in general, they are different. And in general, it's the compactness that's doing the heavy lifting, not the closed and bounded. Okay. So, it actually would be a good use of your time. Go back, after today's lecture, go back and look over your notes or look over the book for when we did this result last semester, and see if you can find the compactness lurking in that proof. Okay. Oh, and by the way, does anyone remember where we used that result? So I'm talking about this result. If we restrict the domain to be closed and bounded, then we have uniform continuity. Does anyone remember where we actually made use of that result?
Didn't we do a lot of like integral stuff with this?
Yep. So it shows up in the proof that continuous functions are Riemann integrable. You need that uniform continuity. Okay. So let's see. We got some metric spaces. You got a continuous function. And the domain X is compact. Then it's uniformly continuous. Note that we're doing the same thing here. We talked about this a little bit last time. I just want to point it out. This theorem might be more applicable than it looks. Let's say your domain is some big space. Okay, how about this? Say your domain is the real line, right? This theorem, as it's stated, doesn't look like it says that you're going to get uniform continuity. Well, the thing is, you restrict your domain to be the compact set, and then you have a compact domain. Okay, so we would consider, if we want, if we've got f of x equals x squared, we would consider the function f restricted to, I don't know, whatever our closed and bounded interval is. And then that is a compact metric space. Okay. So again, this is just kind of a standard way that all theorems about compactness are stated. And it goes back to the fact that compactness is intrinsic, so it doesn't matter where you're looking, compactness means the same thing. So we might as well just restrict our functions to the compact set, and then we can just say we've got a compact domain. Okay? So it's still just as applicable as if we'd said, Right, we could have said, suppose that we have a compact set in X, and then F is uniformly continuous on that compact set. But then we'd have to go and define what it means to be uniformly continuous on a set. You know, usually we don't even give that definition because we just restrict the domain. Okay. I hope that didn't create any additional confusion. Are there any questions before we start the proof? So here's another reason that compactness is a nice thing. When you've got a theorem about compactness, you can usually kind of guess how the proof's going to go. Right? What are we going to do? We're going to make an open cover. And what are we going to do to our open cover? We're going to take a finite subcover. Okay? And then we just got to get the details right. Okay. Where is our open cover going to come from? Well, we're continuous at every point of the domain. So at every point in the domain, we have some delta that's dependent on that point where our function values aren't too different. Okay. Because of what ends up happening at the end of the proof, we're going to divide everything by 2. So these, what it looks like to be kind of gratuitous divide by 2 in the beginning of the proof, they'll all make sense by the end of the proof. Okay. So let's let epsilon be given. That's the epsilon from the definition of uniform continuity. Now, F is continuous on X, so for each point, A in X, there's a delta, but the delta depends on A, so, and now it's going to matter. So I'm going to subscript it by A. And what's the rule? If a point is within delta sub A of A, then its image is within, and this is where we're going to have one of those gratuitous divide by 2. Its image is within epsilon over 2 of F of A. So we've used continuity. For every point A, we've got this delta. So you can think about it as kind of, for every point A, we've got this ball around it where continuity holds. I mean, I guess it's not really that continuity holds, it's that this inequality over here holds. Okay, let's let our open cover be the set of all those balls. So what that means is that we're going to define our open cover to be a set of all balls, except, again, we're going to have a divide by 2. Instead of taking the ball of radius delta A, we'll take the ball of radius delta A over 2. Why is this an open cover of X? So why is that sentence true?
Well, balls are open and A is every point in X. So we cover every point in an open set.
Yep. Yep, just don't forget there's two things there. The openness and the covering. And thank you, Benjamin, I fixed the delta too. Okay, it's an open cover of compact set, so now we take our finite subcover. Okay. Since X is compact, now this is kind of a running theme. When we take our finite subcover, we frequently don't want to just say we've got some finite subset of U. We want to be a little bit more clever. So if you look at how U is defined, there's one set in U for every point in X. So when we get a finite subcover, we're going to get one set for every point in some finite subset of X. Okay, so that's what how we're going to take our finite subcover. It's just kind of an indexing convention that we're doing, and it makes the argument a lot easier to write. So what do I mean? There's a finite subset f of X, so that the set V and these are only the points from that finite subset F that covers X. Any questions so far? Okay, so where are we? We've got our domain X. We've got some finite number of points. And we got some balls around them. And those define some sort of open cover of our space. I don't know that I can really draw a useful picture over here. Anyway, every point is in one of these balls. Maybe I'll draw like, there's a ball, here's a ball, etc. Every point is covered there. Now that means that if I look at any particular point, oh, obviously it's in one of these balls. So this black point that I drew, his function value is within epsilon over 2 of the function value at the red point at the center of the ball he's in. Okay? Now what do we want to do for uniform continuity? We want to say any two points that are close enough have close function values. So I want to look at not just that point, but also any point that's close enough to that black point there. Right, so in this case, why do these 2 points, let's call that X and that Y, why are their function values close? Well, in this particular example, it's because both x and y are close, they're in the same ball of the finite subcover. So as points, they're both close to that red point. Therefore, their function values are both close to the function value at the red point. And then the triangle inequality just tells us that their function values are actually close to each other. Okay. And that was why we did all the dividing by 2, was the triangle inequality that we're going to have to use here. Okay. So that's going to be the argument, and you know, it's not completely clear what the delta we're going to pick is, except I'll tell you that if you go through to the end of the argument, you'll see how you would have to go back and correct it if you made a mistake. Okay. So we're to that point. We need to pick a delta. Okay. We were given the epsilon, and now we need to give the delta, and the delta says if 2 points are within delta, then their function values are within epsilon. I'll just write down the delta. Delta is 1/2 of the minimum of these delta sub a's from the finite subcover. Okay. I think the minimum part of this should be a natural idea, because we've got some finite set of points, they've each got a delta. Since it's a finite set, there is some minimum. So, okay, it makes sense to try the minimum. You know, the 1/2 just comes out of the triangle inequality that we're about to do. Okay?
I got a question.
Yeah.
We're doing just half of the delta, so we're taking the minimum of the ball radii.
Yes, we're taking the minimum of the ball radii, and then we're dividing that by 2.
So is it half of the minimum of delta A over 2? Or is there another half in here somewhere?
Oh, I'm sorry. No, I mean, I'm sorry, yeah. Danielle's a really good point. Why am I writing it this way? Why would I not say, here's our balls, they got radii, delta A over 2. Take the minimum of those. Wow. Okay, now if you look at it that way, assuming that you've explained away the first divide by 2, I think it's even more natural, right? These are just the smallest of the radii of these balls. Yes, and I see that, 20 minutes ago or something, Benjamin wrote in the chat that we're going to take the minimum of these, and that is indeed what we did. Okay. Well, now let's just, all that remains is to prove that it works. We need to take 2 points. I'm using the A's to be the points in the finite subset, so I'm going to take an X and a Y. And we need to suppose that they are within delta in the domain. Okay. Now, it doesn't matter which one. Obviously, X and Y are the same. I mean, obviously, like, X and Y are in the same situation. We're going to pick one of it and then use his ball that he's in to do our argument. So let's do Y. So there is a point A in our finite subset F, so that Y is in his ball. Okay. So what does that mean? That means that F of Y is close to F of A. Okay. Where close to means, we'll come back to this, but close to is this epsilon over 2 up there, which is how we define a delta A. Okay? So f of y is close to f of a. We need to show that f of x is also close to f of a, and then we'll triangle inequality it. Well, we know that x is close to y, so x is also close to a. And that's what I'm going to write down now. This is a triangle inequality. I want to get x close to a, so I'm just going to form the triangle where we go to y first. Okay, and you can see that we know these things. The distance between x and y is less than delta. The distance between y and a is less than delta a over 2. And how can I simplify that? The whole thing is less than or equal to delta a. Yeah? Okay, and just take a look. Delta. How did we define delta? We define delta to make this happen. Okay, and the fact that they are within delta, so x and a are within delta a, and now we get to go back up here to how delta a was defined, and that tells us that f of x and f of a are close. So when we look, what we really want, again, is we want the distance between f of x and f of y in the codomain. We use a triangle inequality to relate that to what we know. We know the distance, we know the distance from each of those function values to f of a. And we got bounds on both of those. Okay. This is less than. The first one is epsilon over 2. And the second one is another epsilon over 2. Okay?
I have a question.
Yeah.
So we said that there's a point A and F, so that Y is in the ball centered at A, of radius delta A over 2. So we only know that the distance between Y and A, okay, delta A over 2 is less than delta A. Cool. Never mind.
Yeah. So I think it comes down to the definition of delta, right?
Yeah.
So that definitely the whole reason we define delta this way is so that later we can say this fact, and that's the fact we need. Any other questions here?
So maybe a more overarching idea. So what compactness is really doing here is letting us take a minimum. That's
Yep.
the important role it's taking.
Yes, yes. And if you go back and you look at the proof from last semester, we do the same thing.
So is that what compactness sort of does a lot? Lets us take a minimum or a maximum of things?
Yeah, compactness is an incredibly broad idea in mathematics. I mean, this is only one. This use of compactness is actually only one kind of aspect of the much more general concept of compactness. But what it always means is passing from the finite to the infinite. Okay, so here we're kind of arguing that, everything is nice on the finite, if we've only got finite in many neighborhoods, so therefore it's nice if even if we've got infinitely many of these neighborhoods. Or when you go the other way around, we've got infinitely many balls, but really we only need finitely many of them, and therefore we can take an actual minimum instead of an infimum. Because notice, again, and this is just a general thing, if you have an infimum instead of a minimum there, things aren't going to work. Because an infimum of a bunch of positive numbers could still be 0. So you might not have that your delta is positive. Okay. One more thing before we call it quits for the week. What's the converse to that theorem?
F is uniformly continuous and F is continuous.
Yep. So suppose that you've got a compact domain. If F is uniformly continuous, then it is continuous. Is the converse true?
Yes.
Yep. So you just look at our definition of uniform continuity, that implies continuity. Okay. So the converse to this theorem is true. So we could have stated it as an if and only if. And if we do it that way, it says, if we've got a compact domain, then a function is continuous if and only if it's uniformly continuous. Okay. So as long as your domain is compact, you really only kind of have that one notion of continuity, and it's the very nice notion of continuity. Okay.
So that means for a compact domain, we can use our fancy topologic continuity definition.
Oh, that's a good point, Daniel. Yes. So as long as your domain is compact, you get to use that one, the open sets definition. Yeah, and you get to use that definition, and you still get all the power of the uniform continuity. Okay, well that is all we've got for today. So have a great weekend, and I will see you all back on Monday.